Hi everyone, it's Miss Cronky. I'm here with your, I can't believe I'm saying this, final video lesson of the year. We're going to be converting rectangular and polar equations. So make sure you viewed Mrs. Hellman's video first. Let's jump right into it. So on the screen, you see the four equations that Mrs. Hellman gave you. These are really important, and these are going to be the same equations that we'll use to convert rectangular to polar, polar to rectangular equations, not just coordinates. So I just want to point out, we've got x squared plus y squared equals r squared. Hopefully that one sounded familiar to you from geometry. It's just the standard form equation of a circle centered at 0, 0. Okay, and then you can find your radius. You've got tangent theta equals y over x. This one you might remember even as far back as Algebra 2. We introduce you to trig functions on the coordinate plane, so you know that tangent is y over x. And then from probably chapter 6, when we started introducing vectors, x is equal to r cosine theta, y is equal to r sine theta. Those kind of sound familiar to us. So these four equations we're going to be using to make conversions. And you're going to see these on each of my slides. Sometimes you could do the conversion of the equation more than one way. So you could choose one equation or a different equation from this list and still end up with the same answer. And then other times one is really probably like the best or more efficient method and the one that you would want to choose. So that's probably the hardest part about rewriting the equations is it's not as always straightforward as the coordinates. You might have to do a little bit of manipulation first. Okay. Let's go ahead and look at polar to rectangular equations. So I have a little note here, like how do you know when you've actually solved it or like made the conversion? Well, you're going from polar, which would have r's and thetas in them, into something rectangular, so you can't have any r's or thetas left. It has to be x's and or y's. And then generally, you want to solve for y. Because if you think back through all your years of math, we've always asked you like solve for y, so that you have y equals. Now, sometimes there may not be a y in your equation, so then you would want to solve for x. And then we know from our previous chapter on conics, there are some shapes that have x and y in them with squares, x squared plus y squared. So if you have an x squared and a y squared in the same equation, generally that's going to be a circle. So you can leave it as x squared plus y squared and try to solve for that piece. Okay, so let's look at the first example here, r equals 3. It's in polar form because it has an r. We want it to be in rectangular form. So we want it to have only x's and or y's. So I'm going to kind of zoom in here. Okay, so I'm looking at this r equals 3. And I'm going to look over here at my options on the left. I can definitely say I'm not going to use tangent theta equals y over x because that equation doesn't even have an r in it. So that's not the route I want to take. So I'm thinking about x squared plus y squared equals r squared. I'm thinking about x equals r cosine theta, y equals r sine theta. Okay, so now, right now, it doesn't look like any of those. In order to make the substitution, I need it to look like r squared, or I need it to have an r times cosine theta, or I need it to have an r times sine theta. Can you think of a way to make that left side with the r look like any of those three that I have highlighted? If you were looking at the first one, r squared, you might say square both sides. R squared equals 3 squared. So now we have r squared, which is really x squared plus y squared equals 9. I had said before when you were making conversions, try to solve for y, but this would be one of those exceptions because I have an x squared and a y squared. It's really a circle. And so I would say this is an okay rectangular equation. Notice it's not polar anymore because it doesn't have r and it doesn't have theta. It's only in x and y's. You may have been looking at some of the other highlights, like maybe you were thinking, oh, I was going to multiply, I had r equals 3, and I was going to multiply both sides by cosine theta. So if I decided to multiply by cosine theta, then I could change this piece right here into x. But on the other side, I don't have a substitution for cosine theta. Cosine theta isn't equal to anything in x and y. So this is probably like not the best route for you to take, because then you still have to try to make the conversion some other way. So that's the part where I'm talking about you might be thinking of more than one way to do it. Sometimes there's one that's really the best way, and this one works out pretty nicely. Same thing if you thought about like how could you get r squared if you were going to multiply both sides by r. You would get r squared on the right, but then you would have it equal to 3r on the, or sorry, you would get r squared on the left, but you would have it equal to, here, I'll write it out. R equals 3. Maybe you thought about, I'll multiply both sides by r, so then I have r squared equals 3r. Sure, you can rewrite this as x squared plus y squared, but then on the other side, you're still stuck with an r. And so it would be like back to square one. How do we change that into rectangular form? So again, not your best option, okay? So you might have to think about more than one way that you would want to manipulate the equation so that you can get out of the r's and the thetas and into the x's and the y's. Next one, theta equals 3 pi over 4. So I've got my 4 equations over on the other side. Note that this one again is in polar form. It has a theta, and I want to change it into rectangular form, so I want it to be in terms of x's and y's. Well, looking at my 4 equations over here, I can say I'm probably not going to use that first one, x squared plus y squared equals r squared, because that equation doesn't have a theta, and I don't even have an r. So I might be thinking about using tangent theta equals y over x equals r cosine theta, y equals r sine theta. If I kind of examine those 3 equations, I guess I'm sort of leaning towards tangent theta equals y over x, only because this equation only has theta, and so does tangent theta equals y over x. It doesn't have an r in it. Whereas if I wanted to use x and y, I'd also have to introduce an r somehow, which probably isn't my best idea. So I want to manipulate this equation, theta equals 3 pi over 4, to look like tangent theta equals y over x. Okay. Well, really, I'm focused on this part right here because I have the polar piece theta. How can I make it look like tangent theta? Take the tangent of the left side, and that's allowed as long as I take the tangent of the right side. So now tangent theta is really just y over x. And then this piece right here, tangent 3 pi over 4, you have unit circle knowledge. What is the tangent of 3 pi over 4? Well, the pi over 4 butterfly has 1 as its tangent, so it's 1 or negative 1. And 3 pi over 4 is in quadrant 2, where tangent is negative, so the tangent of 3 pi over 4 is negative 1. Okay. Now I have this equation, which doesn't have theta in it anymore. It has y and x, so I'm getting closer to something, or I am rectangular now. I'm getting closer to my final answer, but remember I had mentioned if you're changing it into a rectangular equation, if possible, you want to solve for y. So my final step here is I want to get the y all by itself, so I'm going to multiply both sides by x so that I have y equals negative x. And that equation should look really familiar to you. That's actually the equation of a line. It's of the form y equals mx plus b, where your slope is -1 and your y-intercept is 0. I'm actually going to, before I leave these two examples, I'm going to talk just really quickly about the graphs and how they are related rectangular to polar. So if you were graphing x squared plus y squared equals 9 on a rectangular coordinate plane, we know that the center is at 0, 0, and we would say our r squared is equal to 9, so our r is 3, so we would count like right 3, up 3, left 3, down 3, and then draw our round shape. If you're graphing in a polar grid, r equals 3, so you got to think about the grids that you saw with Mrs. Homan. Remember that the r's are part of those concentric circles around the pole. So if your r is 3, that means that when you're graphing that, you would count out from the pole to the third circle, to the third ring. And then we don't know what theta is, like for graphing a point, like we did with Mrs. Homan. We just know that r is 3, so it could be any of the points on that third ring, and you will graph a circle with a radius of 3. So it's the same graph, just in a different system. Okay. Let's see, looking at this one right over here, theta equals 3 pi over 4. Theta equals 3 pi over 4. Think about on Mrs. Homan's system, we have the concentric circles around the pole, and then we have those different like butterfly families. So I'm gonna look at the pi over 4 family. Pretend I'm going through my poles. If your theta is always 3 pi over 4, that's this line over here in quadrant 2, okay? And then we don't know what r is, like what is the radius on this particular equation? We don't know. It's not a point, it's an equation. Theta equals 3 pi over 4. So it could be any of the points over there. And those would be all the points when the r value is positive. So you go in that direction of 3 pi over 4. But if r was a negative value, you go in the opposite direction. So then that would be this piece over here. And so the graph that you would actually do in polar system is a line. Okay. And that matches up to our rectangular, y equals -x. It goes through the origin, its y-intercept is 0, and then it has a slope of -1, so we would go right 1, down 1, and we're drawing that line. So we're drawing the same graph in a different system. Okay. Now these two are nice if you kind of like recognize that r equals 3 is one of the rings, then you know your equation in rectangular form should look like a circle, x squared plus y squared equals r squared. If you recognize that you have a theta equals an angle, that's just going to be an equation in rectangular form for the equation of a line, y equals mx plus b. It's actually going to be a y equals mx because it will pass through the pole if it's a theta equals. And so you can use that going both ways. Okay. You don't have to graph the equations on your homework. These are just two that are nice to kind of see and make the connections from the systems. Okay, let's get back to converting. Okay, so I'm going to do r equals 2 cosecant theta. So again, think about what form you're actually in. This has r's and thetas, so I want to turn it into x's and y's, rectangular form. Looking at my 4 equations, I'm gonna cross off x squared plus y squared equals r squared because that one has r, but it doesn't have theta. I'm gonna also cross off tangent theta equals y over x because that has theta but not r, and this equation has both. So I'm thinking about x equals r cosine theta and y equals r sine theta. You might notice in this equation that you have a cosecant theta, and we don't really have a cosecant theta over here in our options. So maybe first step I would do is change that using my identities to its reciprocal. So if you're multiplying by a cosecant, you're really dividing by a sine. And then that kind of tells me immediately I should be trying to make it look like an r sine theta. Well, right now, sine theta is in the denominator, and r and sine are on opposite sides of the equation. But if I were to just multiply both sides by sine theta, then I would end up with something like r sine theta on the left, and my sine thetas would cancel over on the right. R sine theta equals 2. And now I have it looking exactly as it needs to look, r sine theta, so that I can say all of r sine theta is just y. Y equals 2. So this equation, r equals 2 times cosecant theta, is really a horizontal line in rectangular form. Okay, let's look at r equals 6 cosine theta. Okay, so I'm thinking about this particular problem, and similarly kind of run through your different options. I'm not going to use this equation because it doesn't have a theta. I'm not going to use this equation because it has tangent and then it doesn't have an r. And I'm probably thinking that I want to use this equation x equals r cosine theta somehow. Okay, so as I start this problem, I might be thinking about, well, r is on the left, cosine is on the right. So maybe you want to try to get them on the same side. But if you were to divide both sides by cosine theta, this would turn into r secant theta. And you can't make that substitution. So I don't think it's going to be as simple as x equals 6. Okay, I got to get a little bit creative here. I want it to look like r cosine theta, because if I have r cosine theta, then I can change that to an x. So on this side, I only have cosine theta. It needs an r. So I'm going to multiply it by r. And if I do that on the right side, then I have to do that on the left side. So now I come up with r squared equals 6 times r times cosine theta, which that's what I wanted, so that I could write that as 6x. And then I hadn't really intended this over on the left, but I had to do it to keep the balance of my equation. I multiplied that r by r again, and I got r squared, which I do have a conversion for that. I'm actually using this equation that I crossed out. Okay, r squared is x squared plus y squared. Now, looking over my equation, I have something that is in x and y only. There are no r's or thetas left over. So this is rectangular form. Thinking back to our last chapter that you took the assessment over, conics, this is a circle. Because you have x squared and y squared, they have the same coefficient of 1. And if we wanted it to look like the equation in chapter 10a, this would be what we would call general form. So you just make it equal 0. So like if you have an x squared and a y squared, just keep them on the same side, and you can move over any other x's or y's that are left over. Okay. And you don't actually have to do this every time, but I just want to show that we could change that by using our methods from chapter 10a, completing the square, regrouping our families. What number completes the square here? It's going to be a 9. So this is going to give me x minus 3 quantity squared, and then I'll have plus y squared. And then this 9, I would actually, the minus 9, I would add it over to the other side, so it equals 9. This is the standard form for a circle. Okay. I'm okay with this form right here. X squared plus y squared equals 6x equals 0. Okay. But you could change it into standard form using knowledge from chapter 10a. Okay. So now you would know to graph it, go right 3, up or down 0, and then you have a radius of 3. Count up 3, left 3, down 3, right 3. Okay, let's do some examples now where we're going to switch from rectangular, so things that have X and Y in them, to polar. And similarly, there are like most of the time you're going to solve for R, but sometimes you won't have an R, so then you solve for theta. Okay, that's kind of the rule. So like most of the time we solve for Y, sometimes we don't have a Y, so we solve for X, or sometimes we have an X squared and a Y squared, so we get those things on the same side. All right, looking at my first example, X squared plus Y squared equals 16. You're probably looking at this, oh yeah, that's gonna be an easy conversion. We're gonna use X squared plus Y squared equals R squared. So all of this is equal to R squared. Solve for the R. So we're going to square root both sides. R is 4. Okay. This is very similar to that. I think it was the first example that I did. We have a circle with X squared plus Y squared equals 16 with a center at 0, 0 and a radius of 4. So we count up 4, left 4, down 4, so on. And then in polar form, we have just R equals 4 because we're on the 4th ring. So that is a circle centered at the pole, which is the origin, with a radius of 4. Okay, so those kind of always go hand in hand. Let's do Y equals negative square root 3 over 3 times X. Okay, well, I have X and Y in this equation, but they're not being squared right now. So I'm going to cross off that first one. I don't think that's going to be one that I want to use. If I wanted to use tangent theta equals Y over X, I would need to make my equation look like Y divided by X. Is that possible? Yeah, just divide both sides by X. So if I said Y divided by X equals, and now it would be negative square root 3 over 3. And then because I have Y over X, I can change that to be a tangent theta equals negative square root 3 over 3. And then I don't have an R to solve for. So remember, we would solve for theta. So I want it to be theta equals, if you're taking the tangent of theta, that would mean you would do the inverse tangent on both sides. So I'm going to inverse tangent both sides. And then this goes back to chapter 4. When you're doing inverse tangent, you're answering from negative pi halves to positive pi halves. Okay. Since the ratio negative square root 3 over 3 is negative, we're getting an angle from quadrant 4. So negative pi halves to 0. And what family does that come from? That comes from our pi over 6 family. So the answer to this would be negative pi over 6. Now, technically, there's infinitely many ways to write that polar equation because angles have coterminal angles. Like we could write that as theta equals 11 pi over 6, theta equals negative 13 pi over 6. But we should all come up with the same angle because we use inverse tangent rules. So we're answering from negative pi halves to positive pi halves. This is an example where I could have done this problem another way. I could have used these two equations right here because I had an X and a Y. So I could have done R sine theta equals negative square root 3 over 3 times R cosine theta. And then I would divide both sides by an R cosine theta. So when I do that, my R's cancel out and I have sine theta over cosine theta, which is a tangent theta. And then these guys canceled out totally. So I have negative square root 3 over 3. And I'm back to where I was before. But I think it's easier to go through tangent. So if you see something like this that looks like Y equals mx, just divide by x and use your inverse tangent to solve. So it should look like theta equals an angle in the end. Okay, I think I have 2 more examples. Let's look at y equals -5. This is rectangular. I want to put it in polar. And based on what I have, I don't have a lot of options, right? All I have is a y. So I'm going to make the substitution r sine theta. So where I see y, I can write r sine theta equals -5. So now it at least has polar values, r and theta. But remember, you try to solve for r. So we're going to divide both sides by sine theta. And then r equals -5. Instead of dividing by sine theta, dividing by sine theta is multiplying by its reciprocal, cosecant theta. And we have a nice equation there. You're going to start to see, like I think we did an example with a cosecant theta already. So you're going to start to see like some of the same things, and this will be nice. And you'll kind of make the connection of how you can go in and out rectangular to polar and vice versa. Okay, last one. This one's probably the most challenging just in terms of like if you were doing this for the first time by yourself. So this equation is rectangular, and I'm just right above gonna move that 3 to the other side. Oops. So that I would have 4x minus 7y equals -3. And if you think about this equation in rectangular form, that's a line. In standard form, ax plus by equals c. You could certainly solve so that you could see y equals mx plus b. But the big difference between this line and the 2 previous lines I did was the other 2 lines went through the origin or the pole. And if you solve this one for slope-intercept form, you're going to find out that your y-intercept is not at the pole. So these equations, when you have something that isn't just y equals mx in rectangular form, when it has a b value other than 0, they're not as nice to rewrite, or they don't look as nice in the end. So for this particular problem, what I'm going to use is actually the x and the y's. So I'm going to make the substitution for x, r cosine theta, and I'm going to make the substitution for y, r sine theta. Now I'll have a plus 3 equals 0. So by substituting the x and the y, r cosine theta, r sine theta, I now have something all in polar. So now it's just a matter of solving. And remember, we're going to try to solve for r. So notice that in the equation, 2 of your terms have r, but the 3 doesn't have r. So that needs to be moved to the other side. 4r cosine theta minus 7r sine theta equals -3. And I still have those 2 r's. Okay. And then I have these 2 terms that are being subtracted. 4r cosine theta minus 7r cosine theta, or sorry, 7r sine theta. Well, they both have r in them, so I can factor out an r so that I have 4 cosine theta minus 7 sine theta, and that equals -3. And my whole goal is to solve for this r. R is getting multiplied by this expression 4 cosine theta minus 7 sine theta. So I'm going to divide both sides. Okay, so I'm going to divide this side by 4 cosine theta minus 7 sine theta. And I'm going to divide this side, 4 cosine theta minus 7 sine theta. So this will cancel out. I'll just have r equals, and then I'll have -3 over 4 cosine theta minus 7 sine theta. Can't really break that up or simplify it any more than that. So this is our polar equation. And that's probably the one, it doesn't really like look very nice, but how did I know that I actually like finished the equation? I changed everything into r's and thetas, and then I solved for r because there was an r. Okay. So you give this a go on your homework. It gets better with the more practice that you do. And, you know, be thinking about, like, every time I started a problem, I always had those 4 equations that Mrs. Homan gave us in our video. Okay, they're right over here on the side. So think about these 4 equations. Okay, and which ones maybe are possible choices that you would use, which ones would you definitely not want to use because they're missing something, or how could you manipulate your equation to make it look like that. Sometimes you might start with one and then try something else. Definitely stop by and see us in our Zoom office hours. We would love to see you, or email us with your questions. We're happy to help. And good luck. I will talk to you guys later.